Federated learning tackles privacy, but statistical heterogeneity causes client drift. Prototype methods like FedProto mitigate this by sharing class-level embeddings instead of full weights. But there's a critical flaw, the alignment maturity gap. In early training, local models haven't learned discriminative structures yet. Global prototypes aggregated from these noisy representations are unreliable. Yet alignment pressure is applied from round one. The prototype alignment loss is distance-dependent. The gradient scales directly with the embedding prototype distance. In early rounds, this distance is huge. This generates massive gradients that dominate the cross-entropy signal, suppressing local feature learning and destabilizing optimization. Alignment is applied before representations are mature enough to benefit. FedSAP fixes this with two mechanisms. First, a progressive alignment curriculum. We linearly warm up the alignment weight over a fixed number of rounds. This delays full alignment pressure, allowing local representations to consolidate before being pulled toward global consensus. The schedule is deterministic and introduces no per-round communication overhead. Second, geometry-driven proxy separation. Instead of adding learnable parameters, FedSAP repurposes the global prototype bank as a shared proxy set. We project embeddings and prototypes onto the unit hypersphere. We compute scaled cosine similarity logits to prevent gradient saturation, then apply a softmax cross-entropy loss. This enforces interclass separation by pulling representations toward target prototypes while repelling non-target classes. Ablation studies confirm the proxy separation accounts for the majority of the accuracy gain, while the curriculum provides the essential stability foundation. This structures the embedding space geometrically with zero additional communication overhead. Results across FEMNIST, CIFAR-10, and CIFAR-100 show FedSAP outperforms FedProto and FedMPS, with gains up to 4 percentage points under severe non-IID conditions. The framework also extends naturally to semi-supervised federated learning. By initiating the semi-supervised phase only after the supervised curriculum stabilizes, we avoid noisy early pseudo-labels. For unlabeled data, we use weak to strong consistency. Samples are accepted only if the margin between the nearest and second nearest prototype distances exceeds a calibrated threshold. This ensures high-confidence pseudo-labels and mitigates confirmation bias. FedSAP proves that scheduled alignment is a general design principle for robust federated representation learning.